Okay, cool. Welcome to lecture 20. Pretty crazy. Turn to the person next to you and tell them what you have for breakfast. Go. Anybody have anything interesting? Yeah, what'd you have? What did you say?
I didn't have anything like specifically for breakfast, but I had a taro milk tea.
Oh, very nice. Very nice. Anybody else? I had a cinnamon raisin bagel. Woo. Okay, let's get started. Why, please. Some announcements for you. Kind of same stuff as yesterday. Our final project is due August 4th. Make sure you've met with your TA, and even more so now than yesterday, make sure that you've gotten it approved before you start working, not email somebody ASAP, somebody being your TA, hopefully, or the CS10 email. Homework 5 can be turned in today if you're using 2 slip days. Today is the final day for that. We have our in-lab final on August 4th as well. Again, that is next week, which is pretty crazy. Everything's gonna be fine, but you know, keep that in your head. And the paper final is August 10th, the following, not next week, but the week after. Any questions about all of that stuff? Okay, I am going to be releasing the self-check for this lecture probably after lecture. I'll probably put out an announcement when I do. I just do not have one ready yet. But again, you'll have the slides and recording to look back through if you've forgotten anything. Questions about any of the logistics? Okay. Yeah. Today I want to talk about some cool Python stuff. So this is lecture 5 of the Python series. At which point you kind of, oh gosh, I'm not deleting slides. Why is this not? Oh, it's just the title. Cool Python stuff. Sorry. Okay. So basically, why are we giving this lecture? So at this point, you know most of the Python basics, hopefully most of the syntax, you've done some practice with it on homeworks. Basically, Python is super powerful. We want you to feel empowered to use it in all of its glory. There are so many different applications in the form of libraries, et cetera, object-oriented programming, and essentially, if you have the knowledge of Python syntax in things like lists and recursion and list comprehensions, then you can do just about anything in Python, which is really cool. So we want you to feel empowered to use that ability of yours. What are we going to look at today? Hopefully we're going to look at tree recursion in Python. So does everybody remember tree recursion? We did that mostly in Snap last time. I think we did that right after recursion. Okay, so we're going to talk about that today in Python. Then we're also going to talk about something slightly different, which is trees as data structures, which is kind of a weird thing if you're coming from tree recursion itself. So we're going to introduce that briefly. You're not going to be tested to necessarily implement what we do today. More kind of stuff I'm saying in lecture about what they're used for and why we use them would be what we would test you on these. Hopefully that made sense. What's in scope, because that's what you really care about. Anything I mentioned in lecture, not implementing anything. Hopefully that makes sense. Any questions about any of that? Does everybody remember tree recursion? Also, if you're curious about what's in scope, ask. Does everybody remember tree recursion? Yes. So how do we define it? Somebody want to tell me how we define tree recursion? Yeah.
because if call itself contains two recursive calls or two or more recursive calls with different arguments,
Exactly.
with like different decrements, like -1 or -2.
Yeah, so we'll usually do, when we see more than one recursive call, we call it tree recursion. So when we use recursion more than once in a function, another way to say that is we call the function we are writing more than once in its body and with different parameters. Questions about that definition? Everybody's comfy with that? Cool. Okay. So some examples. Hopefully you remember count change. What about count stairs? Maybe we did that one. I think we did that one discussion, or we will today. Fractals. So the midterm fractal, I think you had to call it more than once. Does everybody remember that? That is tree recursion. Okay. And Fibonacci. So that is also tree recursion. Questions about these examples? Does anybody not remember one? So that I may refresh. What'd you say? Yeah, we're gonna go over the Fibonacci one actually later today. So that's perfect. I see another raised hand. No, okay. I'm actually gonna come back to this later, but there's a really cool visualization for these. So let's write count change again. So I kind of want to refresh your memories on what tree recursion is, how we think about it. And I want to do it using, I'll do it in Python. And I want to walk through the process again. So if you recall, the premise is I have X denominations of money. So nickels, quarters, coin, different types of coins. I need to count out a certain amount, but I want to know how many, not which ways, but how many ways there are to do that. Okay. So let's draw it out. So I have my denominations here and I have my cents here. So kind of have that visualization. How might I represent these? How do I represent my list of denominations? What's a data structure I can use that we know about that I can use to represent a list of denominations? Yeah, a list, precisely. Yep. Okay. What about my amount? Somebody? Yeah, a number. Yeah, it's just a number, right? Okay. So these are my two parameters. So what does my function definition look like? Somebody want to say it out loud? How do I define functions in Python? You've been coding in Python for a while now. Well, a while for this course, not very long. How do I define a function? Somebody.
With a def.
Yeah, a def statement. Okay. Yeah, what else? Yeah. My function is. And then what else? Woo! Yep. Yeah, that's how you do that. So that's what it would look like. So that part's over. Phew. Okay. Now I want to work out a general process. How do I go about doing this, and how should I expect my code to do this? I need to understand this process before I go telling my computer to do it. So what was that?
I have a doubt in the previous slide.
This one?
Yeah, here we like count change. So where's the number? There's the amount.
What about that?
We need
Oh, sorry. I totally wrote these wrong. I don't know why I wrote that like that. Yeah, amount. Sorry. Yep. Okay. Look good to you now. Sorry about that. Good catch. Okay. Assume that we only want to make 2 recursive calls. Okay. How do I do this? Any ideas? Do I remember how this works? If you don't, that's okay. Nobody remember how it works? Okay, I'll do it. So I know that I must be wanting to count change only twice, right? I only want to make calls to that twice. And remember, count change does exactly what I want it to. I'm assuming that I'm taking that leap of faith that count change is going to properly count change for me. But in which two scenarios do I want to be calling that? In which two scenarios do I want to be asking that question? Okay. So the idea here, and the idea for count change that's super important to understand, is that I can focus on one denomination at a time. Okay. I'm kind of also using this idea of understanding how lists work. I can then either, so this is where I break off, this is where I start to make a tree, that I can either make the decision to count using that denomination, or I can choose not to use it. And this whole idea, it's kind of important to also make that connection about how this makes a tree. Maybe you've heard of like decision trees. So like you have a question and then you go down one path, you have another question, you go down a different path, and each of those paths is unique. So if I take one way, there's no possible way to go back and do the other way, unless I want to start a whole new scenario. Questions about that? Yeah, cool. So let's think about this. So I have this. So I have these denominations, this amount. So if I decide to use pennies, I can either choose to use pennies to begin with. So I can say, okay, I'm going to start counting out my change using pennies, but one at a time, right? Or I can choose to skip pennies and move on to nickels. Okay. So what does this look like? What happens in my code when I decide to go with pennies? What was that? I'm not quite there yet. I want to use pennies. I want to use one coin at a time. Because remember, I could use all 37 pennies, but I haven't done that yet. Because I could still use a penny and use other denominations too. So what happens next? Just kind of thinking about the process we've been talking about. I'm choosing to use a penny. What happens next? Not quite. I can't. Yeah. Yeah. So let's subtract off our penny and continue our process, right? So then I would have 36 cents. And I would have the same amount of denominations. So we start to get an idea of what one of these recursive calls is going to look like, right? So once I've used a penny, I need to go ahead and make a new decision. Do I want to continue using pennies, or do I want to use a different denomination, right? Questions about that? Okay. So what's my base case here? If I'm using this process, so if I'm continually using this process where I choose to use my first denomination, or I decide to not, I decide to skip to the next denomination. What are things that could happen? Yeah. Yeah, so our amount becomes 0. That is 1, and I just showed another one. So we could get 0, which means we perfectly counted out that amount of change, and that's a way to do it. Good? Okay. So that is one way to count change, but I also could have a negative amount left. Let's say I used quarters, I used 1 quarter and then I used another quarter. I'm going to be left with negative change, right? So that's something that could happen. Is that a way to count out 37 cents to 2 quarters? No, right? So negative, that is not a way to count change. So I want to return 0 in that case. Another thing that could happen is that I don't have any denominations left. So let's just say I only said I wanted to use quarters and 50-cent pieces. Let's say I found out the 50-cent pieces aren't going to work, and then I have an empty list of denominations. What happens now? Is that a way to count change? Have I perfectly counted out the amount I wanted to count out? Seeing kind of slight shaking heads. Yeah, right. So I want to return 0 in that case, because that's not a way to count out change. Okay. So what's my recursive call? Well, there's one scenario we decided earlier where I want to include my first denomination. And there's another, ooh. Okay, all right, my slides are messy today. But the other is when I don't want to, right? So let me fix that. So when I want to skip it, in which case I'm going to stop looking at pennies, right? And I'm going to start looking at nickels next. So I'm going to throw pennies out of my list. Okay, so let's finally go over the solution. Okay, So this is what it looks like in Python, right? So we decided my def, and I gave better names here. So I've got coins and I've got amount. Okay. If my amount is less than 0, that's negative, and it's a way to count change or not a way to count change. I see him? Is that a way to see like a couple thumbs down? Right, that's not a way to count change. And also, if I don't have any coins left, that's not a way to count change. Okay, so I'm going to return 0. 0 ways to count change if either of these are the case. Okay, but if I've perfectly counted out, what's that?
Can we use like one denominator only one time?
No, not one time, right? So if I decide to stop, if I want to use pennies for that first one, then I'm left with 36 cents. I'm going to do that thing again where I count change, and we'll get to that in a sec. And I'll still have pennies. And so then I can also subtract off again, and I'll have 35 cents. I can make that decision again. Yeah. So we're considering all, hopefully you can see how we're considering every single possibility if we use this kind of tree. Okay. So if I perfectly counted out, I will have 0 left, and I will have perfectly counted out my change. Doesn't matter if it's a penny, a nickel, like weird combination. No. All I care is that I'm left with 0, and I can now count that as one way of counting out this amount of change. Okay. So in the other case, this really crazy long thing is where I do my tree recursion. So again, we have that decision of like skipping my first denomination. And so remember in Python, we can do cool things like this, where we can chop off the first one, and we can do everything after the first item of coins as a new list. Okay. And then just keep the amount the same. So instead of counting out pennies, I want to count out nickels. And then my other scenario here is that I want to keep my denominations the same, and I want to subtract off maybe that first one, like the pennies. That's another way to do it. And so what do I do with these? Remember, these are each returning, a way to count change, whether it's 0 or 1. I want to add these together. And that is my count change in Python. Hopefully you're remembering tree recursion a bit. We're going to do it again today in discussion. And Vedansh actually has a cool question that we're going to work through now. Any questions about this for right now? Yeah.
Okay, we are just having a leap of faith that this is gonna like cover all the scenarios that we like expected.
Yeah, we have to take that leap of faith that count change works exactly how I want it to. And then I'm going to feed it the arguments that I believe will lead it to return the right thing. That I have to kind of make sure beforehand that these two ways account for every single way I could count out change. So that's kind of part of the work of writing a problem using tree recursion. Questions about this at all? About count change? About how I use Python? Yeah. So that would mean that I've perfectly counted out so just to clarify the process a little bit, let's kind of do something simpler, right? So let's say I have 10 cents. Okay, and let's say that I have nickels as my one denomination. Okay, so if I count them out one time, I'm going to subtract it off, so I'm going to use 1 nickel. So my next recursive call is going to look like this. Remember, I always have 2 arguments to this one. So I have nickels, I have 5 cents. So my only choice again is to use nickels or to not use nickels. But we know if I don't use nickels, I don't have any denominations left, and that's 0. That's not a way to count change because I still got 5 cents left. So I choose to use a nickel. So if I use another nickel, I have to subtract it off of here. So I'm left with 0. And I found a way. So I've used 2 nickels to count out my change. That counts as one way like a valid way to count out 10 cents using nickels. Does that help? Kind of. Can I rephrase? Can I explain it differently? You want me to draw the tree maybe? That might be helpful to everyone. Yeah, okay. So let's say 10 cents again. Okay. They have nickels and pennies. apologize to people watching the video. Hopefully you can see this okay. Okay, so remember that we look at trees as like decisions, right? So I'm just a person here. I'm just a guy who's got to make a decision. And we said that we only want to make 2 recursive calls. So we have basically one decision to make. Goes one of 2 ways. So I want to count out these nickels and or this 10 cents using nickels and pennies. But I have to make a decision about how. So I can either make the decision to start using nickels, or I can say I want to stop using nickels, I want to use pennies. So if I go this direction, I'm going to use nickels. That decision tree, right? I have to kind of answer the question in this box to move on to the next thing. And it's kind of chronological, right? So I can go this way or this way. It doesn't matter, but all of these ways are going to be the ways to count change. So not just one, but this is kind of where we start to see a tree, right? So if I decide to do that, if I decide to use a nickel, over here, I'm left with 5 cents. Over here, if I decide to use pennies, I haven't counted anything out yet. I've just stopped using nickels. So I've still got 10 cents. If I decide to go this way again, and remember, going left is using nickels, I will be left with 0. At which point I tell my program to say, hey, ding, ding, you got away. So this is one valid way to do that. Okay, so let's say that I remember this keeps going. So we keep going this way. I could say use pennies. And I can certainly do that. So if I start to use pennies, what's my amount here? What was that? Okay, it's still 5. And then I need to keep going. If I use pennies, or I use empty, in which case, this is not a way to count change. That's one of those times where I return 0. This returns 1. So all these get added up back here. So these branches get added together. That sort of help people understand this. I would absolutely draw it out yourself too. It's really important. Count change is a really good one to understand. And it's like okay if you didn't understand it the first time and that maybe you're understanding it more this time. But we will be testing tree recursion on the final. With that said, I think I'm going to have Vinaj come up with an example problem that you guys can work through. Warning, it might be hard. Don't let that discourage you. We more just want to. Oh, do you want to hop on the Zoom?
Oh,
If you're going to be presenting.
I will be presenting.
Yeah.
Yeah, I can do that.
Let me send you the link. Really quick, I'm gonna pass this over. Sorry.
How are we feeling about the recursion?
Yeah.
Can I say a scale of 1 to 5 on your fingers? Yeah. Can I see thumbs if you understand why sometimes it's better to use tree recursion and why sometimes you shouldn't use tree recursion? Yeah. Not really. Okay. Wait, hopefully, we can talk a little bit about that. Is it recording? Okay,
Yep.
It is. All right.
Yep.
Yeah, I'm
And
unmuted.
you plug in.
Yeah, I also plugged in, but
Okay. Make sure you get that.
oh, that's out. Yeah. Okay,
There we go.
so what I'm going to present to you right now is certainly going to be a little bit, scatterbrained because I didn't really prepare this for lecture. But I do hope that you find this, that you find this aiding your understanding of tree recursion and why we're even presenting this to you and why it matters. So I'll start off by just a quick, understanding of what tree recursion even is. Before we proceed, I like to have definitions. So let's have a flashback to recursion. Do you remember this joke? Can I see hands if you've seen this before? Maybe in my section, maybe on problem 9 of your midterm. Okay, so to understand recursion, you must first understand recursion. Well, what about tree recursion? To understand tree recursion, you must not only understand tree recursion, but also tree recursion, and lastly, tree recursion. Can I see hands if this joke made sense? Does someone want to explain it to me real quick? Everybody here in my discussion section had their hands up. Someone, come on, let's try. G1, do you want to try? There we go. Okay. So wait, your name first, please. Well, your name first?
Oh,
Jose. Okay.
I think it says like more than once.
Yep.
You said
Exactly. Right. Tree recursion is when you have multiple recursive calls rather than just one. But that's not all there is. Okay. Because sometimes this definition can be deceptive. So let's take a more concrete look at what tree recursion really is. So let's define tree recursion. Well, practically, tree recursion, a function that is tree recursive, has recursive calls that consist of multiple calls to the same function. Okay, so I always like to start with a mouthful and then we'll go into an example. Theoretically, it is whenever the solution of one instance of a problem depends on the solutions of more than one smaller instances of that very problem. Okay, my definition, or the way I like to think about tree recursion, is whenever a combination of recursive calls helps me solve a problem, or B, whenever I have choices or options to consider. So this should start ringing a bell, right? All the problems that you've done in lecture today, and I think the last time we spoke about tree recursion, have been partitioning problems, which means you're given some quantity and you're trying to figure out how many ways you can partition that quantity using certain rules and certain choices, right? So in this instance, you have certain denominations of certain coins, and you have this bigger amount. And you're trying to figure out, well, do I want to use a 50-cent coin or do I not? Do I want to use a 10-cent coin or do I not? And then using all of these choices, how many possibilities can I come up with? So anytime that you notice that at some point in your problem solving scenario, you have a choice or you have an option, and you're trying to tally up how many such choices you have, you're more than likely going to be using tree recursion. Can I see thumbs if that made sense? Okay. Perfect. Watching out for choices and watching out for options. Now, any questions about these definitions thus far? And typically I ask for questions before I ask a hard problem. So anything? Feeling good? So let's look at the problem. The first problem is, are the following functions tree recursive? Okay, so look at the function on your screen. It's called foo. It does a bunch of if condition checks, elif condition checks, and returns results accordingly. So now, show of hands if you think this function is tree recursive. Okay. Show of hands if you think it's not tree recursive. And then show of hands if you're not certain. Not sure. Okay, makes sense. Fine. So now, I would submit to you that this function is actually not tree recursive. Because my definition for tree recursion was, and let's go back to the definition, recursive calls consist of multiple calls to the same function, right? In the scenario that we have over here, we have 3 recursive calls. But how many calls to foo are we making in every recursive call? Just one, right? So it isn't really tree recursion. And for a better visual understanding of why that is the case, we're going to jump into an example. So let's look at 2 functions right here. The first function is this function right here in the small box. It's a function that takes in a number n. If the number n is 0, it returns 0. Otherwise, it returns 1 plus the function called on a number n minus 1. So in some ways, this isn't a tree recursive function because in every recursive call, we just have one call to the function we're defining. Can I see thumbs if that makes sense so far? Okay, and then let's try to figure out the behavior of this function, because that's where, the difference really
kicks into play. So let's see what happens if I call this function on the input 5. Okay. Was that really cool what you just saw on the screen? I find it pretty interesting, right? And the interesting part is that not only did it go down the stack, it also went up the stack. Let's play it one more time. So it starts at 5, goes all the way down to 1, but then also goes up. So what's really going on here? Why is it going down and then up? Does anyone have an answer? Or maybe some intuition, Jeevan?
Because whenever we are calling the recursive call, it's like going deeper into the function. Like it's like creating new number, like creating whenever we reach the base state, it's like combines all the previous outcomes.
Exactly.
Like one,
Exactly.
and returns the value of
Yep.
the outcome.
Yeah, I like that intuition. The intuition has to do with frames and how they work. And that's somewhat what's happening. Let's have a look at the diagram, right? I'll try to be louder for people on Zoom. But so first I call the function with the input 5. Okay. The function checks is 5, 0, no. So then I must return 1 plus whatever the output is of the function being called on 4. But let's imagine for a second that I already know what f of 4 is. Let's say I went down to 4, I did all my calculation and I came here. Is there a value I must now pass up to the call of f of 5? Well, I must, right? Because 5, the call to the function on 5 depends on the result of f of 4. The result of 5 is 1 plus the result of f of 4. So f of 4 must pass up its value to 5, and 5 will add 1 to it and return it. Can I see thumbs if the diagram makes a little bit more sense now? And can I see thumbs if you realize why we also go up? Because each call above depends on whatever the one below gave it. Okay, any questions about that? Pedro. In a sense, it's saying, I'm going to wait till you finish your business before I give my answer. Because my answer is 1 plus whatever your answer is. Right? In essence, 5 depends on 4. So 5 must take something from 4. Likewise, 4 depends on 3, and so on and so forth. So each call first makes a call to a smaller value, then waits for its result, gets the result, and then returns its own value. Which is why you need to go down and you need to go up. Okay. But what you will notice is that when we call the function on this input 5, the number of calls to the function was simply 1, 2, 3, 4, 5, and 6. Okay. So for a function where n is 5, we are just making 6 calls to the function, where each call is represented by a circle. So this seems to be growing somewhat linearly. We have n plus 1 circles, but amongst friends, doesn't matter. And like I said before, whenever we're talking about, the growth of a function, we care about orders of growth, which means we don't care about constants and we don't care about factors. 2n plus 3 is the same as 2n, which is the same as n. So drop all the factors, drop all the addition subtraction. Okay, but then let's look at what happens if we have a similar function that becomes tree recursive. So let's look at this function. Well, this function is something, similar to what you've seen before. It says it takes in an n. It says if n is 0 or if n is 1, it just returns the value that's been passed in. Otherwise, it returns a function called on n minus 1 plus the function called on n minus 2. Does anyone know which function this is? What do we think? Fibonacci? Precisely, right? Because it's saying if you're 0 or 1, just return 0 or 1. We know that the 0th and the 1th Fibonacci numbers are just 0 and 1. And every number henceforth is the sum of the two numbers that came immediately before it. So it's a function that will compute the nth Fibonacci number where n starts at 0. Can I see thumbs if that made sense? Also, cool. Yeah. Shinwu, what's up? Yeah, of course. So I am trying to claim that this function right here, the one I have defined, is the Fibonacci sequence. It is essentially giving you the nth Fibonacci number. And what I'm doing here is I'm saying if n equals 0 or n equals 1, just return it. Otherwise, what I'm doing is I'm returning the function called on n minus 1 plus the function called on n minus 2. Now, how do I figure out that this is the Fibonacci number? So it is the Fibonacci function. Well, let me start listing out Fibonacci numbers. First Fibonacci number is 0, then we have 1, then 0 plus 1, then 1 plus 1, and so on and so forth. Okay, and now let's see. If I wanted the 0th Fibonacci number, I would put in f of 0 and I would get back 0. Does that part make sense? Okay, likewise for the first Fibonacci number. But now, what if I wanted the second Fibonacci number? Well, then this function would say it will return f of 0 plus f of 1, which literally just gives me the second Fibonacci number, right? And likewise, if I wanted the third Fibonacci number, which is this right here, which is the result of summing the first one and the second one, well, this would just give me f of 1 plus f of 2. Does this side-by-side comparison aid your intuition? Awesome. Okay, so now the question is, how is this vastly different than having the function that we had before us? Okay, and the answer lies in how the function behaves when we run it. So let's run fib of 5. So you'll notice now something interesting has happened. Our function did not just execute in a line, which sounds similar to linear, right? Which is why we have linear recursion and tree recursion. What our function did instead is it split into two smaller instances of itself, which further split into two smaller instances of itself. And now if I turn this thing upside down, do I get something that mimics a tree? It looks like a tree-like structure, right? But this thing is a root, and then you have so many branches and you have leaves in the last layers, okay? Which is why we call this tree recursion. But more importantly, isn't this function doing a lot more work for the same input for n equals 5? What do we think? Raise your hands if you think that this function is actually doing a lot more work than the latter function when called on the same input. Okay, raise your hands if you're not sure. And raise your hands if you think it's doing less work. Okay, so remember, each call to a function was denoted by a little circle, right? In this instance, when I called the function with n equals 5, I end up with so many more circles than I did in the last call, okay? I'll end up with somewhere close to 32 circles, somewhere close to 2 to the n circles, right? But in the last call, I always ended up with n plus 1 circles, which means in this instance, I'm doing a lot more work. I'm calling the same function a lot more many times than I did in the last instance. Does that help you understand that this actually does a lot more work? Okay, and does this help you understand why sometimes you need a tree recursive function? Because the answer to your problem does not just depend on the answer to one other problem, but rather more than one other problem. Can I see thumbs if that made sense? Okay, most of us seem to be happy with that. So we will proceed. This projector. Okay, what about this function? Do we think this is tree recursive? Can you raise your hands if you think this is tree recursive? Okay, and raise your hands if you think this is not tree recursive. And then raise your hands if you're unsure. Okay, and then for someone who said that this is not tree recursive, do you mind explaining why? Okay, no, we don't want to explain, that's fine. Here's why this question gets tricky. You're almost always used to seeing recursive functions where for one input n, your function breaks down into two other recursive calls, and then so on and so forth. But what was our definition of tree recursion? Was it that each call to a function requires two other calls to operate? No, it was basically saying that every recursive call calls the function more than once, or at least one recursive call calls the very same function more than once. So what's happening here? Each time I call foo on x, I end up calling foo on x minus 1, x minus 2, and also x minus 3. And likewise, right? Every single subcall also makes 3 other recursive calls. Does that mimic our tree-like structure? Does that satisfy every box we had on the checklist for something being pre-recursive? Can I see thumbs if it makes sense now? Okay, so especially for those of you who are uncertain and those of you who thought this wasn't pre-recursive, can you raise your hands if you now believe it is pre-recursive? Or like put your thumbs up if you think it is pre-recursive. Okay, so those of us who were not sure before seem to be doing better. Any questions about this? Okay, so if not, what I will do is, okay, if not, what I will do now is I'll bump into a few observations with higher order functions. Yeah. This one?
Yeah. So
Yeah.
what's the difference between this diagonal and the other one?
Yeah. What's the difference between? Okay, so let's hover onto that point. What's the difference between this example and the next one? My question to you is, suppose I call foo on a certain quantity x. At any point, how many recursive calls will I make when I run through this function once? What do you think? Either this one, or this one, or this one. But there's no way that I can do something that's in an if clause, and also something that's in an elif clause, and also something that's in an else clause. You see what I mean? So based on the condition, only one recursive call is made each time. So the recursion just makes one more call to the function, right? Versus in my other function right here, I always make 3 calls to the same function, right? So it's not like I'm just making one at a time. And remember, the definition was within a recursive call. So within a single recursive call or within our recursive case, we make more than one calls to the same function. Does that make sense?
Yeah.
Awesome. Good question. Any other questions? Okay. So now this one's like, I think this is an interesting problem which will help demonstrate how Python actually runs functions. And I think it's important because higher order functions are intricately tied with pre-recursion. Okay, so let's look at order of evaluation of functions. Credit for this philosophy to John De Niro, because he likes to teach it this way. And in essence, what I'm trying to tell you is, in Python, the evaluation of a function stops if and only if A, we hit a return statement and we execute a return statement, or B, we go through the entire body of the function without executing a return statement. Okay, so this is all I want you to know. If you're executing a function, it only stops if you either hit a return statement or you go through the whole body without hitting a return statement. And now let's look at a consequence of that. So look at this function closely, okay? It's called cascade of n. It takes in a number n. If the number is less than 10, it just prints the number. Otherwise, it prints the number, then calls cascade on n over 10, and then prints the number again. My question to you is, and this is a very challenging question, but it's worth considering. What is cascade on 1, 2, 3, 4 going to do? What's going to happen here? And take like a minute to really, marinate in that definition, because this is worth considering. So function only stops if we hit a return statement or we reach the end of the body. Any ideas? Okay, Cynthia, do you want to try?
It would, 1, 2, 3.
Okay. It'll start by printing 1, 2, 3. Yeah, but then when we start the function, right? It says if n is less than 10, print 10. Well, 1, 2, 3, 4 is not less than 10. But then doesn't it still just print 10? So it would print 1, 2, 3, 4, right? But you have a pattern about where this is going. I like where you started. I see that you're following the flow. Yeah, but that's a good start.
I thought after print 1, 2, 3, 4,
Yeah,
it goes to count. It
exactly,
could be 1, 2, 3.
exactly, right?
And then it prints.
Precisely. Yeah, yeah.
We print 0 at the end.
Will it print 0? Do you think? Oh, so
One.
2 of us are disagreeing. Do you want to try stating why?
Like it will just print like first 1, 2, 3, 4, then 1, 2, 3, then 1, 2,
Yeah.
then 1, and
Then?
it will continue printing 1.
Will it continue printing 1? It's an interesting question, right? So let's like try to hash this out. We start with n is equal to 1, 2, 3, 4. Okay, so that's our first call to cascade. N is equal to 1, 2, 3, 4. First we check. Is n less than 10? No. So we go into the else clause, and the first thing we do is we print n. So let's do that. Let's print 1, 2, 3, 4. Okay. And then what do? We call cascade on n divided by 10. Okay. So now there's an interesting consequence of this. I start a new call of cascade where n now becomes n divided by 10. N becomes 1, 2, 3. The observation here is this call cannot execute till this function stops. Why? We only ever exit what we're doing in a function if we hit a return statement or if we run out of room. Okay. And right now we have to enter this function again and start all over. So let's see what that function does. Well, it says, is 1, 2, 3 less than 10? No. So we're going to print it. So we print 1, 2, 3. We make another call to cascade. This time n becomes 12. Is 12 less than 10? No. So we're going to print it. Start another call to cascade. And now becomes 1. Is 1 less than 10? So let's print 1. But now what happens? What do we think?
I want to give it a try. So,
Yeah.
you know, like it will reprint it again.
Sort of, but in what
Like,
pattern?
1, 2, 3, 4, 1, 2, 3, 1, 2, 1, 1, 2, 1, 2,
Exactly,
3, 1, 2,
yeah.
3, 4.
And let's try to figure out why. It's easy to see the answer if you run it, but let's like think through the logic. Okay. Right now, imagine we were in the case where n was 12. Okay. So it said print n, call cascade on 1. So when n was 12, we printed n, we call cascade on 1. Cascade on 1 printed 1. Now this whole function is over. Cascade on 1 is done. So cascade on 12 can actually proceed. And it can print 12 again. Okay. This is the hard part of the problem. You start at cascade of 12. Cascade of 1 stops, 12 starts again. And you proceed so on and so forth, and you get the whole sequence back. So I know this was a challenging example, and we're just about out of time. So what I will do is I will let you simmer in this problem and the solution and show up to office hours or come to discussion if you have questions. Anything in the last 1 minute before you leave? Okay, thank you for attending lecture.
So self-check is out as of 4 o'clock, so it should be out now.